Hello, and thank you for taking the time to join my presentation. My name is Stefan Mabry, and I'm a computer science PhD student here at the University of North Dakota. And today I'll be discussing the foundational concept in modern computing, virtual memory. This presentation will cover the history, key algorithms, advantages, and real-world applications of virtual memory, highlighting its pivotal role in enabling efficient memory management and multitasking across a wide variety of computing domains. By the end of this talk, you'll have a clear understanding of why virtual memory is essential in the world of technology today. Let's dive in. So virtual memory is a fundamental innovation that allows computers to run efficiently by overcoming constraints of the physical memory. It does this by abstracting the memory environment into a virtualized space, ensuring that programs can execute seamlessly, even when physical memory is limited. Let's start with a brief look at the origins. Virtual memory was first introduced with the Atlas computer in 1962, and the concept was formalized by Peter Denning in 1970 through his groundbreaking paper titled Virtual Memory. So how does it work? Virtual memory combines fast RAM with slower storage devices like hard drives or SSDs, creating a unified memory environment. This method ensures that systems can handle large applications and multitasking efficiently. Finally, abstraction is key. Virtual memory creates a continuous virtual address space, significantly improving program execution by simplifying memory management for both the operating system and developers. With this introduction in mind, let's move forward and explore the mechanisms of virtual memory in greater detail. So let's discuss the pros and cons of virtual memory. While it's an essential component of modern computing, it does have some strengths and challenges. So with the advantages. First, the continuous space constraints are minimized. So virtual memory allows multiple processes to fit in memory even when there isn't enough physical RAM available. It's like having an extra invisible memory bank that ensures programs can run without interruption. Second, the maximum memory restriction is released. This is a critical advantage that enables programs to be larger than the RAM that's available to execute it. It does this by leveraging the storage devices like hard drives or SSDs as an extension of the memory. Without this capability, running large applications would be almost impossible. And then lastly, the increased abstraction. So virtual memory handles the complexity of memory management behind the scenes so that developers don't need to worry about it. This abstraction simplifies programming and makes systems more flexible and easier to scale. And then moving on to the disadvantages. The first challenge is latency. When virtual memory swaps data between storage and RAM, it takes some time. Disk access is significantly slower than accessing physical memory, so this can slow down program execution. Next, we have the risk of corruption of the disk. So using storage heavily for memory operations increases the chance of data corruption. This is especially true during power failures or hardware malfunctions. And then finally, operating system complexity. Implementing and managing virtual memory requires complex algorithms, which adds to the overall complexity of the operating system. While this isn't a deal breaker, it does make system development and maintenance more challenging. So while virtual memory provides incredible flexibility and efficiency, these trade-offs highlight the importance of optimizing its use for specific applications. Understanding both the benefits and the limitations is the key to getting the most out of the virtual memory. Keep in mind, though, that virtual memory is the most used paradigm in memory management, so these trade-offs are pretty minimal. So now let's compare virtual memory to the physical memory operating system on its own. It's important to emphasize that virtual memory isn't a replacement for traditional memory management methods. It's an augmentation that works alongside them. So however, when we look at the physical memory trying to do the job alone, some key differences emerge. So what are they? Physical memory, when we talk about physical memory, we're talking about just the RAM on your system. Virtual memory extends that capacity algorithmically using by leveraging the GPUs and then the hard drives and the solid state drives. Physical memory swaps processes to and from the hard drive only when absolutely necessary, while virtual memory actively uses paging to create regions of various storage media as extensions of the memory. This gives virtual memory more flexibility in handling larger workloads. And then CPU integration. Physical memory has direct access to the CPU, which makes it faster. Well, virtual memory, however, has access. It abstracts to the access to the CPU in the operating system, which adds a layer of complexity, but it also increases the versatility of virtual memory. And then we have the size available for memory. Physical memory is limited to just the RAM, whereas virtual memory expands that limit by utilizing storage space from GPUs, disks, and SSDs. This can make a big difference in handling resource-intensive applications. It's also why your computer freaks out when you've used up most of your disk, because it no longer has access to the space that it used for virtual memory utility. For speed, physical memory is generally faster, except when swapping is needed. Virtual memory, by contrast, is slower because it involves the mapping of regions through segments or pages, and it relies on that secondary storage that's slower. The key takeaway here is that virtual memory complements physical memory. It allows systems to handle more tasks and larger programs. It's not about replacing the physical memory or other memory management strategies. It's about enhancing what's already there. Now let's take a look at some real-world applications of virtual memory. It's a cornerstone technology that enables multitasking, scalability, and efficiency across a wide range of domains. Virtual memory is essential in modern operating systems like Windows, Mac OS, and Linux. It supports multitasking by ensuring that multiple applications can run simultaneously without interfering with one another. It also provides process isolation and memory sharing, which is crucial for system stability and security. Virtual memory plays a huge role in cloud environments. It enables dynamic resource allocation in virtual machines. And it allows cloud providers to scale workloads efficiently while keeping costs down. This makes services like Amazon Web Services, Microsoft Azure, and Rackspace Technology both scalable and cost-effective. And then virtual memory is also vital in high-performance gaming and graphical rendering. It manages real-time rendering by dynamically allocating memory between RAM and GPU, ensuring that both smooth gameplay and rich visual fidelity. It allows modern game engines like Unreal or Unity to handle large textures and models seamlessly, even on consumer-grade hardware. Across these domains, virtual memory addresses memory constraints and optimizes resource utilization, making it one of the most versatile technologies in computing today. So let's walk through the core steps of the virtual memory algorithm. Each step is crucial in ensuring smooth memory management and program execution. The process begins when the CPU generates a virtual address. This address is then translated into a corresponding physical address using the page table. This mapping ensures that the program can access the correct memory location seamlessly. The operating system then uses the page table to determine the mapping between the virtual page and the physical page frame. Think of this as a directory lookup. It tells the system where the requested data is stored. If the requested page is not currently in physical memory, a page fault occurs. This triggers the system to retrieve the required page from the secondary storage, such as the hard drive or SSD, and then load it into the RAM. When physical memory is full, the system uses a page replacement algorithm to decide which page in memory should be evicted to make room for the new one. This ensures that the most relevant pages stay in memory, while the unused ones are swapped out. These 4 steps, translation, lookup, handling, and then replacement form the backbone of virtual memory, allowing it to function effectively while managing system resources efficiently. This slide illustrates how virtual memory takes a seemingly continuous block of memory and then allocates it dynamically across different hardware components like the RAM, hard drives, GPUs, and solid-state drives. So on the left, we see the virtual memory space, which appears to be one continuous range to the programs that are using it. But on the right, we see how that memory is actually distributed across those physical resources. Keep in mind that this is a mock-up or a diagram that I created, so it's not exactly like this, but this is a good representation of it. So, for example, the most frequently accessed data is allocated to the RAM because it's the fastest. And then less frequently accessed data might be stored on the SSD or the hard drive, which is slower but provides that much larger storage capacity. Then for the graphics intensive applications we talked about, some memory might be mapped to the GPU, which has the specialized memory optimized for high performance rendering. The operating system and the virtual memory algorithms handle this allocation seamlessly, ensuring the right data is in the right place at the right time. This flexibility allows the systems to maximize performance and the resource utilization without requiring developers to manage memory directly, which is tedious. The key takeaway here is that virtual memory creates the illusion of continuity while optimizing the use of all of the available hardware resources. To conclude this presentation, let's have a few key takeaways. Virtual memory abstracts physical memory constraints, enabling multitasking, efficient resource management, and improved system performance. It's the backbone of modern computing, ensuring seamless operation even with limited physical resources. We've seen how virtual memory is vital across domains, whether it's in the operating systems or cloud computing or gaming, or even advancements in AI. Its versatility allows it to handle diverse workloads efficiently. While virtual memory offers significant advantages, it's not without those challenges. So the latency from disk swapping, system complexity, and the risk of data loss during failures poses an ongoing hurdles that engineers and developers must address. Looking ahead, innovations in unified memory systems and faster technologies promise to enhance virtual memory scalability and efficiency, ensuring it remains a critical component of future computing systems. Virtual memory's ability to balance flexibility, efficiency, and performance is why it continues to be a cornerstone in computing technology. These are the citations that I used for this presentation. I'll pause here for a second if you want to take a screen grab, or if you want to pause it. I guess the key one on here will be the Denning paper I mentioned. Virtual memory is right here, and you can take a link to that paper. This is normally where I ask questions for Q&A, but you can reach out to me in the comments. Also, you can find me on LinkedIn or my email address, or visit me in Madison, Wisconsin. Thank you for joining me for this presentation, and have a great day.